Hello, and welcome to Organic Chemistry with ItsDrDan. And this is our first episode of how we are going to be explaining introductory organic and biochemistry, mainly aimed towards allied health majors and the health sciences. So, with this particular playlist, as I begin to make it, it's going to go through fundamental skills to be able to help you with just the introduction and basics behind organic and biochemistry. So, only the fundamentals. It's not about trying to go through arrow notation and every little detail. It's just how to go through basics. So where does it all start? So with this, it's all about the chemistry of carbon. So carbon is the center of our world. No matter if it's organic or in biochemistry, it's all about carbon. And what really, if you can kind of remember from your basics from general chemistry, what made carbon so important was its ability to be able to make bonds. And if you can remember, carbon in particular has 4 valence electrons around it, meaning that it can make 4 bonds around on all sides. And that's what we're going to be focusing on today as we go through this. So let's first take a look on if we can make 4 bonds with carbon, what other important bonding trends do we need to know before going into organic chemistry? Okay, so with bonding trends that we are going to commonly see, so most of these are based off your periodic table, where there are trends that show how many bonds. So with organic chemicals, most of them are dealing with carbon and hydrogen, particularly hydrocarbons, which we'll talk about later in this video. So carbon, as I said earlier, it can make a total of 4 bonds. Now, what else is there? Well, hydrogen was another common component. Well, hydrogen can make up to 1 bond, and that was due to its 1 valence electron it had. So hydrogen could do 1, and carbon could do 4 that were all around it. Now, how does that trend continue? Well, if you kind of can think about it, well, nitrogen is right next to it, and that can do a total of 3 bonds around it. Oxygen can do 2, and all of the halogens on the far right-hand side of the periodic table can all do 1 based on the number of bonds that they all have around them. So if you can remember those little trends, that is what we're going to be using to help us go forward with all these different parts of the class, depending on how many bonds you exactly are making. And here we have all the individual Lewis structures for each of those individual species as well. So let's go on to what other things we have to know about organic chemistry. So when it comes to organic, the other thing is how are you going to be seeing molecules in organic? There are 4 different ways that you're going to see this. The first way is chemical and molecular formulas, which is from the same thing as general chemistry. So molecular formulas are all referring to, let's say if I had either a 2-carbon species like ethane, which we'll talk about the naming in future videos, so C2H6, or let's say with methane, CH4, or C3H8 for propane, we can show all those individual structures via their formula. However, this does not tell us any of the particular bonding patterns that we see within these molecules. They just tell you how many carbons, how many hydrogens. But a big component of this is how does it bond? In organic chemistry, that is what we want to know. So there's 3 ways to show how something is bonding. The first one is complete structural formulas. It's also sometimes called line bond or full structures as well. So if we're to use, let's say if we use the example that I have on the right-hand side here with propane throughout this, so how would we show that complete structural formula? Well, we would show our carbons all bonding together, being that this is the chemistry of carbon. We're going to constantly be showing chains of carbon connecting together. We'll then have our hydrogens fill in the rest. So remember, we have a total of 4 bonds on every single carbon, and we can show that as well. So we will fill all those in. And just to look at, let's say if I look at the first carbon here, we can quickly count all the bonds around it, right? We see 1, 2, 3, 4 bonds all around that carbon. And we can do that for every single one of those structures that we draw. We're always counting to the magic number 4 as we're going through them. So now with condensed structure, the way to think about this one is if you're playing a game on your phone and you have to collect different pieces to almost in a sense to collect tokens or bounties or all kinds of things like that. Well, this is the same way. Essentially, if I take and I click each one of my carbons here, and I want to minimize them to help make this condensed, we can show that as well. So if I have my first carbon, right, so the CH3 on the end, so that was this carbon here, we can minimize that all down. Now, if I go to the second carbon, we can do the same thing as well, where we show CH2. And then I can do it again on the third carbon to show, okay, we have CH3, CH2, CH3. Now notice if I number those 1, 2, and 3, it's showing that bonding pattern and it's minimizing all those individual structures. Skeletal formula is the last way, which is the easiest out of all of them. It's the same thing as saying geometric, because all we're going to be drawing is lines to show the different bonds. So what do I mean by that? Well, if I want to do propane, which is 3 carbons, this is all I would show, is just like this. Now, what exactly is that showcasing? Well, each of these little vertices or corners represents a carbon, okay? And it's assumed that they have all 4 bonds around it, meaning that this has its respective number of hydrogens with it as well. So if I wanted to expand that a little bit more, I could show that, all right, well, I have CH3, CH2, CH3, or we can even try to expand that a little bit more, because not only is it showing the geometries behind this, but we can also see the total of number of hydrogens as well. So the correct one is the one all the way up in that top left-hand side, but we can, this is the idea behind geometric. It simplifies it, but it still shows all of our numbers of hydrogens that we have here as well. So let me move that over so you can see that behind me. And we can easily showcase all those little pieces. Let's do an example together. So if I say let's do an example, let's say we want to find all those little pieces for C4H10, also known as butane. So with this one, first thing is, well, how do we find the molecular formula? Well, we're given it, right? So C4H10 would be our answer for that first part. Now, the complete structural formula is the whole idea is showing this in like a 90-degree, completely expanded out form. So complete structural, line bond, expanded formula, these are all referring to the same thing. First thing we start with is writing our 4 carbons in a chain all together. And now what we're going to do is we're going to fill in all of our hydrogens along with that. So we'll do that in a different color. And we have 1, 2, 3 hydrogens all on the first carbon. Notice how there's a total of 4 bonds there. So I'll even highlight a little bond here in yellow just to show that. And then for our next one, I'll do that in different colors as well to help illustrate all the bonds. So notice how it's 1, 2, 3, 4. Then we'll go to the next one, right? 1, 2, 3, and 4. And then we'll finish our last one by filling in all of the hydrogens in another color. So we have 4 bonds on each individual carbon for that complete structural formula. Now, the next part is, like I mentioned, it's like clicking each of these little carbons. So clicking carbon 1, 2, 3, and 4, and minimizing them. So how would we do that? Well, the first one, right, we'd have CH3, and then we'd have CH2, and then we would have CH2, and then CH3. So trying to color code that so they stick together, right? You see that minimization that's occurring. The skeletal formula is just doing our little zigzag pattern. And the whole reason we're showing those zigzags is because it shows geometries, which we'll cover in future videos as well. So talking about tetrahedral geometries for this particular one. So being that we will have this, it'll be 1, 2, 3, 4. And just to kind of tell you, right, this represents that CH3, CH2, CH2, CH3 behind that particular structure with this zigzag pattern. And we can even put that in the individual lines to help illustrate that as we are going to do that in this course or this understanding of organic chemicals. let's go on to the next topic. In organic chemistry, what we're going to find out is that all these molecules are hydrocarbons, meaning that they're mainly made up of carbon and hydrogen. These are revolving around three major types of hydrocarbons. The first one is referring to all alkanes. Alkanes are telling you that they're all single bonded carbons. Alkenes are double bonded carbons. And then alkynes have a triple bond in between those carbons. And what we're going to be looking for as we're writing these hydrocarbons is if it has one of these different types of species inside of their chains, which we are going, as we draw them, if you have one of them, that tells you the type. Now, one thing that you can maybe take a notice of is what is really different between all these, and that is the ending here, right? So we have ane, ene for alkane, alkene, and alkyne. Well, what these have to tell you about is that, well, when we are looking at all these different chains, also known as acyclic chains as well, so they're just a continuous chain, or not a branch. When we have them, they have different endings behind them. So all these individual endings, and here we're going to move this down. So with all the endings, they tell you exactly what is important about them. So their ending or suffix in the name, which is going to be important in part 2 of this. It tells you their functional group or their organic family, which gives you an idea of really what properties are they capable of as we are going through all these little individual types. So it's something that is extremely important for our understanding of how they are going to behave as a chemical compound. So let's look at this a little bit further. And some other different pieces of information that you're going to commonly hear in organic chemistry is referring to something known as the longest carbon chain or the parent carbon chain. So what this is referring to is whenever we are looking at an organic hydrocarbon or structure, we are always looking for the longest chain. So for example, going through these, there's a long list of them. Here's the first 6 of them. Generally, we go up to the first 10 for us to be able to look at them. Let's draw the geometric structures. So the first one is methane, which we don't bother drawing the geometric. We just write CH4, but we can even go past that. The next one, ethane, is 2 carbons. So ethane is referring to whether you write it as just CH3, or it can also be written as a line illustrating that structure. With propane, that was the example that we first did, right? That looks like almost like a little arrow, and that's showing that CH3, CH2, CH3. Butane, right? We're going to still take that same shape, but we're going to add one more carbon onto it. And the same thing with pentane going down, right? We're just increasing the length of the chain. And the same thing with hexane. We are just increasing that length by 1 carbon each time. And we can show that each one of those little corners are 1 more carbon as you're going through them, right? We're going to consistently count all of our carbons as we are looking at the parent chain. So as you're going through these examples, you're trying to figure out, okay, what is your longest chain as you're going through these? And that is one of our key takeaways. What else will we see other than parent change is going to be something known as substituents. Let's go on to the next thing. The last key word that we're going to show in this video is different branches or substituents, which is a common thing you're going to see connected to all of these different parent chains or longest chains. So there are a bunch of common substituents. Yes, here I have 4 of them listed, which are methyl, ethyl, propyl, and butyl. And these are alkyl chains. So notice that it has that YL ending here. What this is referring to is that, okay, this is a branch. So it's something that's almost like an extra piece or appendage to our longest chain. Let's take a look at this. So let's say if I draw pentane here, let's show some examples of different chains. So if I go off this first part here where I have just a methyl attached to this, so it's a CH3, this is an example of a methyl chain. We could continuously add to this as well. So let's say if I wanted to make this a little bit longer and do the next one, which is ethyl, well, all we would have to do is show that chain increasing in size, just like this. And what this here is showing that, all right, well, we have a CH2, CH3 substituent, which is known as ethyl. Now, that can continuously grow even farther, possibly. So let's say if we had a longer chain here, and I decided to add a 3-carbon chain to the end, which is 1, 2, 3, this would be an example of a propyl. Okay, so that would be propyl, right? So 3 coming off. And then as you can kind of imagine with that trend there, if we have a 4-carbon one coming off, or our branch coming off, then that's going to be butyl. So 1, 2, 3, 4, all coming off of that chain, right? So, and that would show the last one, which is a butyl group. Now, typically they don't usually get longer than butyl. Butyl is typically the maximum, being that it's all about what is your longest parent chain. And as we're going through, this is a basic introduction of our different verbiage that we're going to be going through this video series. We're going to go into our next video, which is going to be all about functional groups and how we can see how this is going to define not only what your chain's name is, but also the properties behind it as well as we go through all these different series of videos. All right, thank you for stopping by, and I hope you check out part 2. And this has been Dr. Dan. Please hit that like and subscribe button, and I hope to see you again next time in the future. Bye now.